பென் டிரைவ் வேணும், இந்த எல்லோ பென் டிரைவ். பின்னாடி ஒரு sir. Shall we get started? Those are online. Am I audible?
Yes, sir.
Why half of you are at home? Holiday na?
Yes, sir.
Yes, sir. இதுல நிறைய காட்டுவேன் நான் விஷுவல்ஸ். Okay. See if you're able to understand. Date என்னடா? 20?
8.
சரி, ரெடியா? Shall we start?
Yes, sir.
See, you guys tell me, are you able to see the board clearly or is it up? Sorry, observe it clearly. Sorry. So did we solve these problems? Tell me. In the previous class, did we solve problems? One problem. Is it from textbook? This one only, no? This is the formula I gave you. This one only. I'm asking, did I give you problems based on this? Did I give you these formulae? I don't remember. See, why I'm asking is both the batches parallel, it is going on parallelly. That's why I'm confused. Did I give you these formulae? Did you all make a note of it? You're done. So no doubt, right? Can we just summarize what we discussed in the previous class and then get started with the main points? So what is the first thing that we saw in the previous class? We understood, we saw that simulation, right? Through that simulation, what was the important point that we could observe? It's not motion of magnets. It is changing something. So for you to generate EMF, that is for you to generate potential difference, you need to create a change in flux with respect to time, right? So if there is a change in magnetic flux taking place with respect to time, then you can induce EMF. That's the whole crux of the story. Second point is, when that EMF is getting created, it is observed that the EMF is directly proportional to the change in magnetic flux. You either write it as delta phi by delta t or d phi by dt, right? But we put a minus sign before that. Why do we do that? We put a minus sign to indicate that it is a significance of some law. What law is that? Lenz's law. So what does Lenz's law state? For that also, we saw the simulation. If you see, when you move the north pole closer, the current got induced in such a way that the induced current generated north pole. So when you moved the north pole closer, the current in the coil was in such a way that the north pole got generated and it was trying to repel it. When you moved the south pole closer, what happened? South pole got generated. When you moved the north pole away, south pole got generated. When you moved the south pole away, north pole got generated. Meaning, if you were trying to increase the flux, what do you mean by increasing the flux? If you were trying to increase the flux by pushing the pole closer to the pickup coil, what happened to it? It was trying to oppose it. In the sense, when you try to increase the flux, it generated the same pole so that it tried to decrease. When you try to decrease, it tried to generate the opposite pole so that it was trying to increase. So whatever you did, it will exactly do the opposite job. That is the reason why we put this minus sign. That is the significance of Lenz's law, right? And one important point to be noted here is Lenz's law is based on the conservation of energy. Please make a note of it. Did I tell that point? Write it down. So Lenz's law is based on the conservation of energy. Clear with this point? Right. So shall we proceed with some problems? Right. Because when you try to increase the flux, right, you're trying to do some work, right? It is trying to decrease the work in such a way that it is compensating. That is the reason why we say it is based on conservation of energy. Okay. Did we do this problem? This is the last problem we did, no? Yeah, I remember this. 3 cases, no? Right. Shall we start with the second problem? Right. So listen to this. So problem number 2 is, a small piece of metal wire is dragged across the gap between the pole pieces of magnet in 0.5 seconds. Okay. So a small piece of metal wire is dragged across the gap between the pole pieces of a magnet in 0.5 seconds. There are 2 poles, right? Between these 2 poles, there is a gap. In this gap, there is a coil that is moved in how much time? In 0.5 seconds. So when the coil is moved, what is going to get changed? Magnetic flux will change. But I'll give you an idea of how you are supposed to think to solve any problem, irrespective of. So let me put it in this way. Instead of saying problem, right, I'll give you an idea of how to think the change in magnetic flux is taking place for a problem or for a derivation also. Okay. So the point that you need to think of is flux is equal to BA cos theta. This is the only formula we have. Magnetic flux is equal to BA cos theta. So if the flux has to change with respect to time, remember this flux can be a function of only one parameter. The flux can be a function of only one parameter. So flux should be a function of time. Why I'm saying flux should be a function of time is EMF is equal to d phi by dt. So you can differentiate something only with a function of that variable. So phi t is equal to, when I write this BA cos theta, right, there are 3 parameters that are involved which decides the flux. One is magnetic field, one is area, and one is theta. So out of these 3 parameters, any one of the parameters can change and the other 2 will be a constant. Are you able to understand what I'm trying to say? So what will generally happen is, if B is a changing parameter, if the magnetic field is changing with respect to time, area and the orientation of the coil, that is theta, will be the same. If area is changing, B and theta will change. If theta is changing, B and A will be the same. So that is how the concept is designed, or that is how you design the system itself. Okay. Now, my question in this is, why I told you the story is, even before you complete the question, right, completely read the question, you have to think of the fact whether there will be an EMF induced or not, right? So what are they saying? There is a small piece of metal wire which is dragged between the gaps, dragged across the gap between the pole pieces of a magnet in 0.5 seconds. So there is a gap and the coil is moved. When this coil is moved, can you tell me out of these three parameters, which parameter is changing? When the coil is moved, what is the parameter that is changing? It is area. Because between these two poles, there is a constant magnetic field existing. B is not changing. You didn't move the magnets. Magnets are at that place. So the amount of field lines released from this and the amount of field lines received by this are the same. They are constant. What about theta? Theta is going to be the same. But what is moved? The coil. When the coil was outside, what was the flux through the coil? Or what was the area that is associated with the magnetic field? It is zero. Whereas when it started moving inside, the area increased. Due to the change in that area and magnetic field and orientation being constant, in this case, the flux is changing. So here, flux is a function of time. So is the case with area. Are you able to understand? So, see, for this problem alone, I'm explaining in depth because I'm going to use the only logic to solve the problem or to derive anything that is there. Okay. Next is the magnetic flux between the pole pieces is known to be 8 into 10 power minus 4 Weber. Estimate the EMF induced in the wire. So when they say that the magnetic field between the pole pieces is known to be 8 into 10 power minus 4 Weber, that is the amount of flux that is going to get associated with the coil as soon as it enters the field. So what is the change in flux taking place through that coil? So change in flux is going to be 8 into 10 power minus 4 Weber. And if you observe, I wrote delta phi here because the time is a measurable quantity. I will write dt had they asked instantaneous value. I will write delta t if it is an average value. So what is delta t here? 0.5 seconds. So what is going to be the EMF? So when they say EMF, right, mostly they'll ask only about the magnitude. So EMF is equal to, actually it is minus n into delta phi divided by delta t. If you take the magnitude, and since this is a small piece of metal wire, right? See, but the question is slightly ambiguous. They didn't tell whether the metal wire is actually a closed one or an open one. I'm assuming that everything is closed here. So if it is closed one, then this is valid. If it is open one, the EMF generated will be zero. Because for open circuit or for an open wire, there is no flux that is defined. Right? So I'm assuming it is closed because here also they use the word only wire. They didn't use the word coil. So I'm assuming that it is closed. Okay, let me check this. So this is equal to n is there, no? So n is going to be only 1. Delta phi is how much? 8 into 10 power minus 4. And how much is going to be the time? 0.5. 0.5 is half. Half 2 will go to numerator. So it will be 16 into 10 power minus 4 volt, provided it is a coil. Okay, let me check the answer. Yeah, they considered it to be a coil only. So 16 into 10 power minus 4 or 1.6 into 10 power minus 3. Both are same. I mean, clear. See, mostly they will write it in terms of multiples of 3 because 10 power minus 3 is milli, 10 power minus 6 is micro, 10 power minus 9 is nano, and 10 power minus 12 is pico. They'll mostly write it as multiples of 3. I hope I'm clear.
Sir, you are not audible.
Sir, you're not audible, sir.
Oh, sorry. முடிச்சதுக்கு சொல்றேன். Shall I go from the beginning for them? One more time? Yeah. For their benefit, I'll go from the beginning. So listen. The magnetic flux through a coil perpendicular to the plane is varying according to the relation phi is equal to phi t cube plus 4t square plus 2t minus 5 Weber. Calculate the induced current, right? You need to calculate the induced current through the coil at t is equal to 2 seconds if the resistance of the coil is going to be 5 ohm. So what do we mean by at? At means instantaneous, right? Between means average. At means instantaneous. So for that, what are we supposed to do? So since they are expecting the current, I is equal to E by R. So can I write this as 1 by R into EMF? I will write it as d phi by dt because it's instantaneous value. And secondly, if you observe, when they've given you the total flux itself, we don't know the number of windings or anything. So we'll only be concerned about the value of flux. So you need not write n there. 1 by R is going to be how much? 5 into d phi by dt. So derivative of this with respect to time. So what is the derivative of phi t cube? It is going to be 15t square plus 4t square is going to be 8t plus 2, right? So this is going to be the value of current that is generated at 2 seconds. So current induced at 2 seconds. So current itself is going to be a function of time. So what are we supposed to find? We need to find I of 2. So what is I of 2? It is going to be 15 into 4, 60 plus 2 into 8 is 16 plus 2, the whole divided by 5. So this will come out as 78 divided by 5. And how much is this value? 19 point something. 38. So 19.6 volt is the answer. Sorry, not volt. Correction. 19.6 ampere will be the answer. $15.6. It is 78 by 5. 80 by 5, 20. 16. Oh, sorry. Yeah. I took 100 in the mind. Sorry. I took 100 by 5 in mind and I was calculating. Anyways. So correction. This is going to be 78 divided by 5. This is going to be 15.6 ampere. Am I right? Okay. So those are online. Could you understand? Those are online. Could you understand?
Yes, sir.
Okay. So it is 15.6 ampere. Shall I proceed? Now, fourth problem that is based on magnetic fluxes. A square loop of side 10 centimeter and resistance of 0.7 ohm. So there is a square loop of side 10 centimeter, which is going to be 10 into 10 power minus 2 meter, right? Which is 10 power minus 1 meter. And there is a resistance of how much value? 0.7 ohm. So there is a resistance of 0.7 ohm. Is placed vertically in the east-west plane. It's placed vertically in the east-west plane. A uniform magnetic field of B is equal to 0.1 Tesla is set up across the plane in the northeast direction. So when they say northeast direction, right, the first point that should come to your mind is angle between the magnetic field and the aerial vector will be 45 degrees. Because this is north, this is east. Northeast is exactly an angular bisector of north and east. So it should be this 45 degree should come to your mind. Am I clear with that? Okay. So is set up across the plane in the northeast direction. The magnetic field is decreased to 0. So initially the magnetic field was 0.1 Tesla. This is B initial. And B final is how much? It is decreased to 0 Tesla. Right? In how much time? In a time of 0.7 seconds. Okay. It is 0.7 seconds at a steady rate. Determine the magnitudes of the induced EMF and current during this time interval. Right. So EMF is equal to, can I write it as delta phi divided by delta t? Because they use the word loop. Loop means there is only one turn. Coil means n turns. Right. So delta phi by delta t, I wrote it without a minus sign because they asked the word magnitudes. Right. So delta phi by delta t means, now tell me, I told you in the beginning, phi is equal to BA cos theta. So if phi has to change, any one of the parameters has to change and the other two will be a constant. Here, what is changing? Magnetic field is changing. It is going from 0.1 to 0 Tesla. Right. Area is constant and theta is constant. So how much is delta phi going to be? Can I write it as A into cos theta multiplied with B final minus B initial? What I actually wrote is the same formula. What I did is phi final is going to be B final into A cos theta, because A is same, theta is same. Phi initial is how much? B initial into A cos theta, because they both are same. That is what I took here. So final minus initial. So I took A cos theta outside, B final minus B initial, the whole divided by delta t. I hope it makes sense. Now, if you see, they told it's a square loop, but they gave only the side. So for a square loop, what is going to be the area? It is going to be A square, and cos of how much should I write? 45 degrees into B final is how much? 0 minus what is the value of B initial? 0.1, the whole divided by 0.7. Am I right? So A square means how much? A is 10 power minus 1. A square will be 10 power minus 2 into cos 45 is 1 by root 2 into this value is going to be 0.1. I am ignoring the minus sign because again it is magnitude. The whole divided by 0.7. Now remember, 1 divided by root 2 is 0.707. This is a famous value. You learn about this in the next chapter. 1 by root 2 is 0.707. It's very simple because you rationalize it, root 2 by root 2. So it is going to be root 2 divided by 2. What is the value of root 2? 1.414 divided by 2, which will be 0.707. Right, it is 0.707. Put it there. So this one will be 0. I'm approximating to 0.7 itself. Divided by 0.7 into 10 power minus 3. This and this will get cancelled. So answer will be 10 power minus 3 volt or 1 millivolt. That is going to be the amount of EMF induced. So once I find the EMF, the next question they have asked is, what is the induced current? For which we need the resistance. So resistance is given as 0.7. So what is going to be the induced current? So 1 divided by 0.7 is going to be the answer. Right? So induced current is equal to induced current is equal to E divided by R. E is how much? 10 power minus 3. The whole divided by R is how much? 0.7. But I told you 0.7 is 1 by root 2. So 1 by root 2 means 10 power minus 3 divided by 1 by root 2. Root 2 will go to the numerator. So root 2 into 10 power minus 3 ampere. Or it is going to be 1.414 into 10 power minus 3 ampere. Am I clear? Right. So this is your textbook problem. இந்த சாப்டர்ல மோஸ்ட்லி சி பேஸ்ட் இது பேஸ் பண்ணி வராது, கம்மி தான். But you have other topics called as self induction and mutual induction. You would have learnt in your 10th grade. Mutual induction ஒன்று இருக்கும், ஞாபகம் இருக்கா? One coil will be there. See, you would have forgotten. Okay, it's fine. There is something called as mutual induction. Magnetic effects of electric current chapter. Where? They taught you, huh? For what? Self-induction research. You did it in lab, huh? You just gave it. Activity ka? Self-induction and mutual induction is what we'll learn. Those are online. Are you done? Those are online. Are you done copying?
Yes, sir.
right? Try this. So I'll give you 2 minutes time. You try it on your own. But this time what they are asking is, see, find the EMF generated in volts, it's fine. But the next question is not about the current. It is about the charge. I is equal to Q by T. So Q is equal to, first find the current, multiply it with time, that will be the answer. You learned about series and parallel, right? This is how they are. Actually, I don't have bulbs now. Those are online. You can have a look at it. So this is the thing. When the cells or bulbs are connected in parallel, what happens? All the three will be connected with the same wire. You look at this red color wire. If you take red as positive, 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 and positive are connected. Negative, negative, and negative are connected. So they'll be in series. When you connect the bulbs and try to press this button, right? They all will glow with the same intensity, because same amount of voltage is given to each device. Whereas if you take the bulbs in series, right? If you take the bulbs in series, right? What will happen is positive of one is connected to the negative of the other, negative of the one is connected to the positive. They'll be connected in such a way that current through this has to go to this, and through this it has to go. When you press it, right? The first one will glow with a, see, each of them will glow with a different intensity. Why that is happening is because the potential difference is shared. So out of the current and potential difference, which is the most important parameter? For you to have maximum intensity, what do you need to have? You need to have maximum voltage supplied to the device. Similarly, this is what is mutual induction. There is an example of electromagnetic induction. You're able to see this coil. These are problems like there is a coil that has n number of turns, n number of turns. This is a coil. Copper coil is used. You're able to see it? So what will happen here is, this device is connected to a battery, right? This one is directly connected to bulb. So first one is connected to battery, and the second one is connected to bulb. So when you switch on the battery here, what will happen? When you switch on, what will happen? First, the current will flow through this, right? When the current is flowing through this, what will happen? There will be an increase in flux. So there will be an increasing flux that will take place with respect to this coil. So when there is an increase in flux, what should happen to this bulb? It should glow. Did you see? It is glowing, but it is stopping. Why? Because the increase in flux is not taking place continuously. I'm showing it for you only. You ask what you don't know to do for self-induction. So for self-induction, instead of 2 coils, you will have 1 coil. Why it is called as self-induction is because the change in current through the same coil will induce a current in the same coil. So here you have 2 coils. No, instead of 2 coils, you will have 1 coil. Actually, what will happen is, when you switch it on, right, there is current flowing through this. No. Actually, though we call it as mutual inductance, current is changing within this coil also. There is self-induction also taking place. Try to understand. You will understand it when I discuss the theory. I have to show you the diagrams and all, but I'm just giving you the outline. Okay. When you switch it on, the current through this, see, before you switch it on, what is the current through this coil? 0. When you switch it on, what is the current through this coil? Some value. It will increase from 0 to, let's say, 2 ampere or 0.5 ampere, some number. So between that 0 to 2.5, 0 to 0.5, what is happening is there is an increase in current taking place in this. Am I right? So when there is an increase in current taking place, there is a magnetic field inside this coil also, no? Because it is a coil. You know that the magnetic field will be present inside the coil also. So due to its own current, for growing between 0 to 0.5, what is changing within this? Magnetic field within this is changing. So when magnetic field within this is changing, there will be an EMF induced in this coil also. So the magnetic field getting induced within the same coil due to the change of its own current is what is called as self-induction. If the change in magnetic field, if the change in current in one coil is generating the change in flux in the other coil, you call it as mutual induction. Mutual means you need some interaction. Are you able to understand this point? Right. So having said that, now I think you will be able to better visualize what these coils they are speaking about. You're able to see them, no? A 10 ohm resistance coil has 1000 turns, and at a time 5.5 into 10 power minus 4 Weber of flux passes through it. If the flux falls to 0.5 into 10 power minus 4 Weber in 0.1 second, find the EMF generated in volts and the charge flown through the coil in coulomb. So let's see how to solve this. A 10 ohm resistance coil has 1000 turns. So resistance of the coil is 10 ohm. What are the number of turns in this? 1000. No, 10 power 3, yeah. And at a time, and there was some instance where the value of magnetic flux was how much? 5.5 into 10 power minus 4 Weber. If the flux falls to, if the final flux is how much? If the flux falls to 0.5 into 10 power minus 4 Weber in how much time? In 0.1 second. So whenever they use the word in, it is average. Whenever they use the word at, it is instantaneous. So in 0.1 second, when delta t is going to be 0.1 second. Find the EMF generated in volts and the charge flown through the coil in coulombs. What is this? EMF is equal to N into delta phi divided by delta t. What is the value of N? 1000. That is 10 power 3 into what is the value of delta phi? So phi 2 minus phi 1. Out of phi 2 and phi 1, what is the parameter changing? The magnetic field. So I can write B final minus B initial into A cos theta, the whole divided by delta t. They gave flux directly. So it's my mistake. Sorry. My mistake. I should have written phi A and phi. Yeah. So this is the initial flux and this is the final flux. So what is the change in flux that is taking place? It is 5 into 10 power minus 4 into the number of turns is going to be 10 power 3, the whole divided by what is the time it takes? 10 power minus 1. So it is 5 into 10 power minus 4, sorry, 5 into 10 power minus 1, and 10 power minus 1 goes to a numerator as 10 power 1. So answer will be 5 volt. EMF generated is going to be 5 volts. And what is going to be the charge in it? So charge is equal to current multiplied with time. But what is current? EMF by resistance. So E by R into T. So E is 5. How much is the time? 0.1 seconds, which is 10 power minus 1 into how much is the time again? Resistance is how much? What is the resistance? So it is going to be 5 divided by resistance is 10 into how much is the time it takes? 10 power minus 1. So 10 will go to the numerator as 10 power minus 1. So answer will be 5 into 10 power minus 2 coulomb. Right. So 0.05 coulomb, and the value of EMF is going to be 5 volt. Is that point clear? So don't worry, in these problems, you need not be much concerned about the minus sign, because minus sign has a significance which you are going to learn now. What I mean by that minus. Shall I proceed? Okay. So these are all few more problems that are based on the same concept. I don't want to do the repetitive thing. Okay. Those are online, there is no response at all. Are you able to understand or not?
Yes, sir.
So this is the one we solved. You remember? So there is an NCERT problem. Yeah. So now I'll explain you some problems that are based on Lenz's law. Okay. So if you look at this example 6.4, right? So if you look at this example 6.4, this is something that is based on the concept of Lenz's law. Okay. Listen to this carefully. So the question says figure 6.7 shows planar loops of different shapes moving out or into a region of magnetic field which is directed normal to the plane away from the reader. Determine the direction of induced current in each loop using Lenz's law. Right. So I'll give you the steps that you're supposed to follow. Whenever you're solving a problem based on Lenz's law, the first step that you need to follow is understand what pole you are. So first step is understand what pole we are. Okay. So how to find that? Thing is, in this problem, if you see, the field lines are drawn into the plane of this board. Actually, when you're solving the problem, you're going to look at your notebook. So it is going to be into the plane of your notebook. Now tell me, out of the North Pole and the South Pole, which pole has the tendency to receive the magnetic field lines? South Pole will receive the magnetic field lines. Having said that, since this board is receiving the magnetic field lines, since the field is into the plane, I am the one who is emitting it. So when I face this side and look at the board, what pole do I belong to? I am the North Pole. So in this case, what am I? I am the North Pole. Is that point registered in your mind? Second. The second point that you need to observe is find how the flux is changing. So find how flux is changing. So when I say how flux is changing, we know the formula flux is equal to BA cos theta. And when this formula is applied, one of the parameters should change and the other two should be a constant. In this case, if I look at all the three scenarios, right, what is constant? The magnetic field that is received by the board is constant because they have given uniform magnetic field, right? Secondly, it is in the same direction. Orientation is not changing. But when the coil is moving into the magnetic field or out of the magnetic field, the area that is associated inside the magnetic field is changing. So here, which parameter is changing? It is the area. So that clearly tells me if the coil is entering or leaving, if the coil is moving in such a way that there is an increase in area taking place, can I conclude that there is an increase in flux taking place? There is a decrease in area, obviously decrease because they both are directly proportional. So once you figure out this thing, the third point that you need to figure out is the flux decreasing or increasing. So if the flux is decreasing, then the pole generated in the coil, will be opposite to what we are. Meaning, I'm not concerned whether the flux is decreasing or increasing. What I mean by this point is, listen to this carefully. If the coil is moving in such a way that there is a decrease in flux taking place, then what pole do I belong to? I am north pole in this example. So if the flux is decreasing in that coil, then opposite pole should get generated, meaning south pole should get generated. Whereas if the flux is increasing, same pole as what we are will get induced. So if the coil is moving in such a way that there is an increase in flux, then it will generate the pole of what we are. In this case, it should generate north pole. Am I clear with these three steps? See, are you clear with the second point? If area is increasing, flux is going to increase, area decreases, flux decreases. So look at the motion of the coil in such a way that the area is decreasing or increasing. I'll directly solve it and show. Listen to this. If suppose the coil is moving into the plane, is the area increasing or decreasing? The area that is associated with the magnetic field is increasing. So the amount of flux through this is increasing. So if the amount of flux through this coil, the first coil, is increasing, it should generate the same pole as what we are. Because what does Lenz's law state? If you move the magnet closer to a coil so that you're trying to increase the flux, then same pole will get generated. If you try to decrease the flux, opposite pole will get generated. So having said that, since the flux here is increasing, it should generate the same pole as what we are. In this case, we are north pole, means this will generate north pole. But the question is, determine the direction of induced current in the coil. They didn't ask what pole is getting generated. So for the fourth step, what we are supposed to do is, if it is going to be north pole that is getting generated, then the current is going to be counterclockwise. If the south pole is getting generated, then the current is going to be clockwise. So you yourself tell me what is going to happen in this scenario. So here, since it is north pole that is getting generated, there should be a counterclockwise current flowing in the circuit. So when I say counterclockwise, the current should be in the direction of A, B, C, D, A. So start with the same point and end with the same point. So current in this case is going to be A, B, C, D, A. So if you observe, right, these two steps are fixed for the remaining two problems also. Now we are clear that I am north pole. The coil is facing me, right? Now the only thing I'm going to check is the third and the fourth point. So for this coil, the flux is decreasing because it is moving out. The amount of area associated with this coil is decreasing since it is moving out. Since it is moving out, flux decreases. So what pole should get generated? It should generate opposite pole of what I am. I am north pole. This should be south pole. If it is south pole, it is clockwise current. So what is the direction of current here? A, C, B, A. What about this? It is moving out. So when it is moving out of the magnetic field, flux is decreasing. Flux decreases, opposite pole of what we are. North, it should be south. South means clockwise current. Answer will be A, B, C, D, A. That's it. Are you able to understand these points? So this is the whole algorithm, I'll call it. These are the steps that you need to follow to solve any problem that is based on Lenz's law. This is not specific only to this problem. You can solve any problem. But these 4 steps are to be followed in the correct order. Is that clear? Make a note of it. Are you clear with this point? Right, there are actually two more problems that are based on the same concept, where one is 6.5 and the other is the first problem of exercise. The first problem of exercise, we have 6 problems. If you're able to answer correctly for those 6 problems, you have understood 90% of this chapter. So it become very simple. Okay. So those two things alone, I'll do it in the subsequent class. Okay. But revise these concepts and come. So if it's a holiday, we can have it in the morning, right? Tomorrow. But I told you after math class only I can update you. Okay. So those were online. Any questions?
No, sir.
No, right? Okay. Shall we wind up? Do you have any questions? You're clear? Right. So you try to answer the next 2 problems. See if you're able to understand them. So is the light too bright for you? I need some feedback. Are you comfortable with that? It's not too bright, no? Because there is white. I'm having a lot of brightness. Is it? Oh, you're fine for it. If anything of that sort, no, please let me know immediately because I'll change the slide colors accordingly. If there is any discomfort, don't hurt your eyes. Okay. And for those who are online, right? Are you guys there? And for those who
Yes.
are online, like the slide colors are fine, or do you have any discomfort in your eyes? They're fine?
It's fine.
Fine, right? Okay. Okay. So we'll stop with this and we'll start the remaining problems tomorrow. So tomorrow you guys ask me for this thing also, no? Velocity selector and that other. See, that's fine. I'll still teach some other time. This is more important. Okay. Shall I close?